Okay, hello everyone, and welcome to the end-to-end AI. We're currently in the model training and experiment tracking. Once again, thank you all for joining, and if you know you've not completed your assignment, ensure you do that. We are also apologizing for the poor quality we offered a few weeks back. We are trying to get things in order because we are just getting started. So, to go straight ahead to today's activity, first, before we talk about the model training and experiment tracking, we first have to look at the theoretical part of the algorithm we are going to use. So today we are working on binary classification, and first we take a look at what classification is before we talk about binary classification, which is a type of classification. So classification is basically the division of data sets or group of items into distinct categories. So imagine having a collection of cats and dogs, and you want to classify them such that you have cats and also you have dogs. So that is classification. But then our machine learning cannot be 100% accurate. There's tendency that one or two dogs may find themselves in the category of cat, and one or two cats may find themselves in the category of dogs. But then our concern is to have a high level of accuracy. We know we can't get 100%, but we want to maintain some certain level of accuracy. So when we are talking about classification, it can be applied to structured data like tabular data. It can also be applied to unstructured data like text, images, and so on. So when we take a look at the types of classification, we have binary classification, multi-class classification, multi-label classification, and imbalance classification. We are not going to take an in-depth look at all of this. We are only going to focus on binary classification because the data set we are dealing with is basically for this purpose. So we want to be able to predict whether a customer will subscribe or not. So when we have two class labels, that is referred to as binary classification. But when you have multi-class, you have more than two classes to classify. Let's say in a situation where you are now having, let's say, three classes, you are now having goat, cat, and dog. That's a multi-class, and then you can have more of that. So we now have the multi-label classification, which is somehow similar to multi-class, but then we're talking about one or more classes to be predicted, unlike in multi-class where we're talking about two or more classes. So we have the imbalance classification. This is for data sets that are not balanced. In a situation where you have 1 and 0 and you realize that you have more samples of 1 compared to zeros, and then you want to classify them. So such is known as imbalance classification. So the application of binary classification can be is applied to email spam detection. We want to know, is an email a spam or not a spam? Customer churn, we want to know if a customer will churn. We want to be able to predict if a customer will leave or it will be, or he or she will be retained. Customer subscription, which is our own focus for this project, to know if customer will subscribe or not. And then conversion prediction, to know if we'll be able to convert maybe a customer, let's say convert a customer or not. So which is very similar to customer subscription as well, but then maybe we're talking about at this stage we're talking about services. So you want to be able to promote a customer from one phase of your subscription, maybe from the basic to premium. So you want to be able to predict that. So taking a look at the chart on the right side of the screen, what we realize here is that the vertical side we have 0 and 1, and at the middle we have 0.5. So this is the idea of logistics regression, which is an algorithm for binary classification. it is based on probability, the probability that an item will fall into 0 or 1. So we have to calculate the probability. Then if the probability is above 0.5, the item will be classified to be under 1. If it is below 0.5, it will be classified to be under 0. So testing methods for binary classification, we have to be able to evaluate our model after training. We have to be able to say, okay, this is performing well, this is not performing well, this is what we should do, and that is what we shouldn't do. The first thing about classification problem is that every time you want to test it, the first thing people go to, or the most easiest way to test it, is using confusion matrix. So on the right you can see the confusion matrix. We have the actual data, and then we have the predicted ones. So we have the actual positive, which is also referred to as true positive, and then we have the predicted positive. So now when you take a look at predicted positive against the actual positive, you have the true positive here. And yeah, oh, let me correct myself, I think I made a mistake. When you have the actual positive is not the true positive, rather it was a mistake there. So actual positive against the predicted positive, you have your true positive. Then actual negative against the predicted negative, you have your true negative. Now the definition on the left is showing that true positive, this is the number of instances that are positive and are classified as positive as well. But the ones for the false positive, this number of instances that are negative and are classified as positive. I hope you can see, you can get the basics here. If it's positive and it's classified as positive, that's true positive. But if it is negative and is classified as positive, that is false positive. The same thing applies to negative. If it is negative and is classified as negative, that is true negative. But if it is negative and is classified as positive, we know what that is. So those are the ways of measuring the performance of a classification, binary classification problem. And upon this confusion matrix, more can be done. There are other things to be considered, so we're going to take a look at them. One is the binary classification test, and the other one is receiver operating characteristics curve. So for the binary classification test here, we're talking about the classification accuracy, the error rate, sensitivity, and specificity. The classification accuracy here is true positive plus the true negative. By now I assume you know what true positive and true negative is, divided by the total instances. So true positive, we are talking about the number of the actual positive, and they were also predicted to be positive. So plus the instances that are negative, which is actual negative, and they were also predicted to be negative. So when we add those instances together, we divide it by the total instance, the total sample space, the total data. So what we'll have is the classification accuracy. Then when we now consider the false positive, which is the ones that are negative but classified to be positive, we add it to the ones, the false negative, which is the ones that are positive but classified to be negative rather. So when we add them together, the false positive and false negative, we add them together and then divide them by the total instance or the total sample space as well. Then the sensitivity is now the true positive divided by the positive instances. So the ones that are classified at this point, let me quickly take a step back. So true positive divided by the total divided by the positive instances. So we come here and said, okay, true positive, this is true positive. So divided by true positive and false positive, add together, all the positives add together, we divide it by it. Then what we'll have there is is sensitivity. The same thing with true negative for specificity. We take the true negative, then we divide it by the total negative instances that occur under our confusion matrix. This will help us to understand how the classification, how the model is performing in terms of classifying the samples or the data points. So then we take a look at the receiver operating characteristics curve. On this, we have it's actually quite simple, though it may not appear to be so. We have the chart of true positive rate against the false positive rate. Now, what are we aiming at? Our point here is that this curve, this blue line or green line, and the yellow line are good ROC curves. So the better it goes closer to 1, or the more it goes closer to 1, the better. So if it gets to 1, that is a perfect classifier, which is something that is not it's not possible. If you get that, something is wrong somewhere. You have to check your data point again. You have to validate your data and then retrain your algorithm. So the more it goes close to 1, the better. But that is on the vertical axis. But if it's going close to 1 on the horizontal axis, it's telling you your algorithm is trained poorly. So your model will not perform as it should. Then algorithms that can be used for binary classification, we have the logistic regression, we have the support vector machine, which is not really being used anymore. We have the Bayesian classification, then we have decision trees. So in our case, we'll be using logistic regression, and for your assignments, I will adopt an ensemble method, random forest, for you to just try out and see. So this is all for the theoretical part that we need to explain. So we'll be heading straight to the hands-on session, where we'll take a look at the code and how it's working. So okay, here the data set is gotten from UCI machine learning repository, and of course we have to acknowledge the people who worked on it to make it available. So first we import the libraries needed just for pre-processing and visualization. Then hit enter, we run it. Then the data on my local computer, the data is stored under document project EagleSense Q1 cohort dataset cleaned. So the data you got from your last assignment, which is this is the last assignment. Yeah, this is the last assignment here. So if you do it well, you're supposed to save the data at the last part. So the data that you saved is what you now call on this new notebook here, and then we start working on it. So we randomly display 5 point, and then we move ahead to check for missing value, none available, and then we decide to replace -1 with 0. Why are we doing that? If you look at P for days, we have days that are -1. It's not good for our machine learning model. We have to do something about it. So it's better we replace it with 0. Then the next thing, we encode the month feature. So the month feature, which is this, so we encode it. When we encode it, we also display it so that we know which month has which number. So April is 0, August is 1, December is 2, and so on and so forth. So we select other categorical features, which we'll use one-hot encoding for as well. In this case, job is one of the feature, marital, education, default, housing, loan, contact, P outcome. So we use the pandas get dummies method, then we use that to perform one hot encoding on the data set. But mind you, this, don't get too religious. In my opinion, I decide to go this way. You may decide to pick this month and bring this month here, and then make everything one hot encoded. All right, it's not a problem. It's all about your choice. Then I created a small function here, a simple function. The essence of this function is to encode our variable here, our target variable, which is y. Will they subscribe or not? So we encode them. We said no will be encoded as 0, and then while yes will be encoded as 1. So you can see here, no is encoded as 0, and then anything else which is yes will be encoded as 1. So we applied it on our data set on that particular column, which is the target column. So we tried to picture the display the what's it called, the columns, to see what we have, and then we apply the describe method from pandas on it to see the statistical analysis on our data. So we have the 25 percentile, 50 percentile, 75 percentile minimum, and then the maximum, the mean, and then the count. All the data points, I think they are the same because no missing value or something. So we have 44,599, and then for the mean, we can check the mean for age, we can check for balance. The essence of all this is to be able to see if there's possibility that we spot outliers as well. But then we are not going in depth to carry out statistical analysis, right? So we move ahead, then we try to plot a correlation diagram, which when we do, we see the relationship. This is our target value y. Then we see how y has been doing with other variables. I think the worst variable y has the variable y has a worse relationship with is p outcome unknown, and that guy has many samples, dominates the data set, the unknown p outcome unknown. So we can't even think of removing it because that's like more than half of the data set, but yet it has poor relationship with y. And other ones seems to have good relationship. The ones that have the best relationship, I think this that is duration has a good relationship with y, our target feature. If you also come here, this guy, the second to the last, p outcome order has a good relationship with y. So this is just to see help us identify how good the data point is. The data points are correlated, rather the features are correlated. As you can see on the right side, the lighter it is, the strongly correlated the features are. Then the dark the intensity of this color, the deep side of the color shows you that they are less correlated, while the light side shows you that they are highly correlated. So we come here to try to see if we can do some feature importance. Oh, I think I have not been running this code. Okay, so this is where we do this, and then we check for missing value, and then we replace minus with 0, and then we encode our data. Okay, our month feature, we encode it, and then we go ahead and perform one hot encoding on other features, and then we also encode our target value. Then after that we view this guy. Okay, then we perform we try to see a statistical summary of the data. Then we plot the what is it called, the correlation plot. Then we perform feature importance. We want to see which features are more important in this. This will help us to carry out feature selection, to drop some unnecessary features we don't want. So we use random forest to carry this out. Once we've dropped, we've selected our target, and then we dropped our target from X. So we come here and then we split the data into 80 against 20. That was just my doing. It can be 70 against 30. It's all based on what you want. So here we go ahead and run this guy, random forest classifier, using RFE for our feature selection. So when we run it, this may take a couple of minutes. What will happen is that it will try to run some computation and see which features have a good relationship with each other, then rank them. So after that, we print out the features, and then we see which ones are more important in their order of ranking. So from there we go to our algorithm training. So by looking at the feature selection, we may decide to drop some, but in this case we are not dropping anything. We're just going to continue. It's just for you to understand that yes, you can perform feature selection, and the essence of it is to know which features are important and which features are less important for you to drop them off. So this may take a couple of minutes. I will not be able to entertain this, so we'll come back to that. Then we have libraries imported. In our case, we are sticking to logistic regression as agreed earlier, and we are using pipeline to create an ML workflow to hook up the standard scaler with the machine learning algorithm, and then we train. So here we have the data, our X and Y. Ideally we shouldn't be doing this anymore, but I mean, just for posterity's sake, just to make things clear, let's assume that nothing has happened above the notebook, right? Let's assume that we don't know what happened there. We are starting afresh with the algorithm training. So come here, and then we split the data into 70 against 30. Once we do that, okay, this hasn't stopped. I wanted to go ahead and so once we split this into 70% for training and then 30% for testing. So we do a value count on our Y train, which is the target. We see that the ones who did not subscribe are like 27,000 clients. Really, we shouldn't call them clients, potential clients rather. And then only 3,500 subscribe. So this is an imbalanced data set. So by mere looking at this, we already know that our algorithm will perform poorly. Alright, so the best thing we need to do now is to just we'll continue this way, but on a real world problem you have to find a way around this, and the best way to go around this is either you downscale or you upscale. Since you're using machine learning, you're not using deep learning, you don't need much data. You don't even have up to 100,000 data points. At least for deep learning you need like 100,000 data points and above. So in this case, what we'll do is that we undersample, we downsample the data, right? What is meant by downsampling is that we select 3,500 of this zero, then we retrain our algorithm. So instead of having 27,000, we'll now be left with 3,500 of this, and then we'll now have the same data point for zeros, the same number of data points for zeros as well as for one. In some other cases, you may decide to upscale, or let's say oversample. By what I mean by that is that this one you may decide to take it from 3,500 to 27,719, so that they will be at the same level. But for me, what I think is best for this case is undersampling. Bring the one that is 27,000, bring it down to 3,500. So but we are not doing oversampling, undersampling. No, we are just walking ourselves through the entire AI machine learning project pipeline, just for us to see how it is. Then when it comes to the challenges that comes with it, that's a separate thing on its own. So has this hasn't finished running? Will I say my computer is slow? No, I shouldn't say that. That would be embarrassing to the laptop. So let's keep moving. We'll be back shortly. Then we get here where we'll have our pipeline. We'll have the logistic regression and the standard scalar all fused into steps, and then we use pipeline to we pass it as a parameter into pipeline, and then we fit the X train and Y train, and then we use the trained algorithm, which is this module here. We use it to predict X test and say what do we have. So after we've done that, we can also decide to print out the parameters of our logistic regression and see what is in it. So there's nothing much in our logistic regression. It's just the basic logistic regression we are using. We didn't pass in any special parameters also. So we can decide to now run our classification report, and when we do that, you see that because of the oversampled or sampling bias that we are experiencing here, we have 27,000 for 0 and just 3,500 for 1. Because of that, when you see the precision for 1 is very poor and for 0 is very high. The same thing for the recall and the F1 score. So you can see the support. This one has 11,000 and this one just has 1,500. So if you look at the weighted average, the accuracy here is telling you 0.9 or 90%, and you'll be like, wow, that's good. If you look at the weighted average, you will also be like, that's nice. But that's not the case when you look at the classes. One class is performing better than the other, which is class 0 is performing better than class 1. So we have to find a way around that, which is undersampling of our data. Okay, it has finished running, so we can just quickly run this, and then it prints it out for us. We have age, balance, day, month, duration, campaign in their order of that's in descending order. So we import this library, and then we split our data, and then we see how the data is the target is distributed, and then we run this guy, which is the training of our logistic regression algorithm, and then we try to check the parameters in it in our logistic regression. We didn't pass in any special stuff, so we shouldn't be expecting anything. What is there is just the basic parameters, default parameters rather. So we run the classification report, and then this is what we have. Then we go ahead and run plot the confusion matrix, and you see this. Now here, the predicted versus the actual. We can see that for 0 we have very high number, but when you come for 1, this is 1 here and 1 here. All we have is so small. So this is a sampling problem. There is already a bias here. Okay, so it has to be fixed. It also applies to the false positive and false negative. It applies to them as well. It's just that it's not as much as we are experiencing with the true positive and true negative. This adjacent side, our 1 we can refer to it as the true positive. Then our 0, this is 0 here, 0 on the horizontal, 0 vertical, we refer to that as true negative. Then if you take this adjacent side, what we have here is false positive and then false negative. So then we come down here, you have your exercise like I explained last week as well. Your exercise is going to be part of the notebook. So we explain the class, we explain the notebook during the class, then you go back, you rerun the notebook, try to understand what was done, then you find your exercise in it and then do it, instead of you having your own separate data which will be causing confusion. You and I will be using the same data set, right, to go through the entire process. So your exercise 1 is train the random forest classifier. Do not forget to import the random forest classifier. So you have to import it. If not, I don't know, maybe it will run, maybe it will not run. But if you check, no, I shouldn't be telling you that. It's an assignment, so do that. Then there are some things where you see question marks like this on quote, you are supposed to replace it with the right code that should be there. So go ahead and do that, solve it, and then when they say predict as well, you can see this, put the right code in there and then run this cell. Once it runs and everything is fine, you are good to go. So exercise 2, display the classification report for this particular line of code. Then we have exercise 3 as well. We can plot the confusion matrix for this random forest. This one, what did okay, logistic regression. Okay, so that's that for that. Now we want to track the experiment with Neptune. We are supposed to do this with Neptune and MLflow, but let's do Neptune. If everything goes well and you submit all of your assignments next week, before we start talking about deployment, we'll try and work on MLflow just for us to have the feel of it, what it is and how to use it. So tracking experiment with Neptune. The first thing you do, you go to your Neptune environment or platform. This is Neptune platform. Create a new project. In my case, I didn't I use an existing project. Okay, so let's say EagleSense. So let's say this is our project. This is private. If you want only you to see it, and you can also make it public if you want everyone to see it. You can also include your description here. So once you do this, you create. So you click save. Now it is created. So what you need from here is the API token, which is this, and then the project name, which is this. You need both of them so that you take it to our notebook. So if you come here, I'm going to change mine because the one I used earlier is for a different project, and I'm going to delete all of them. So if you think you are going to use my API to attack me, don't worry, it won't be there. So the token will not be there forever for you to attack. Alright, okay, so we drop this. Okay, that's fine. So I've dropped the token, then the name of the project, I copy it and come here and also include it. So this is what Neptune we use to initialize. So once I've done this, I can now delete this guy off my track. So these credentials are what Neptune needed. So we just go here, we run this library and our pipeline, which contains the standard scalar and logistic regression. Then we come here and initiate Neptune, or So we already have the project name and then the API token. So run it. So it's now connected to Neptune and it's telling you remember to stop your run once you finish logging your metadata. So after you finish your experiment, you are expected to stop it. Then now we are assuming that we've not done any training before, so we create our train test split again. Then we decide to save our data, each of these train test, X train, Y train, we save them locally. And then the next thing we do, we start everything in the folder where we save it. The folder where we save it is called cleaned. So everything in that folder will be moved to Neptune. So all we need to do is run. It's a clean data set. That's what we are calling it on Neptune. So to track files, which is this folder. So we'll do this, and then it has run. So if we go to Neptune now, we'll find it. But before we go, let's run other things we need to do. We need to train our algorithm and log the result of the algorithm on Neptune. So we just run this again. Okay, to train the algorithm, collect all the parameters and then store on Neptune all the training parameters and test results, all of that. So we stop. So we have stopped the experiment right now. So having done this, we'll come back and look at the exercises. So let's quickly go back to Neptune. This is Neptune. I refresh this, EagleSense. Okay, it's telling us that we have a run. You can see it here. So we click on it. Okay, so this is all metadata. If we go to, this is what we call it in our notebook, clean data set, if you remember. Where is it? Let me show it to you. Okay, here is it. This is what we call it on our notebook, clean data set. So we move everything on the clean folder up there. So we go back to Neptune and then we click on clean, and then we can see them. The cleaned CSV, that's the main file itself, the X test, X train, Y test, Y train, everything is logged on to this, and the total size is 7.7 MB. So we also take a look at the classifier, then we take a look at the parameters. So for the linear regression, because I am using linear regression, so your own case will be different when you are using random forest regressor. So the scale, everything was logged in here, the weight and all of that. So the parameters for the classifier for the algorithm were logged here. So if you come back and check your diagnostic chart, the class prediction error, it has a chart for it. It will show you. Then the classification report, it will also show you the classification report. I believe now you understand what classification report is. The confusion matrix, it will also show it to you, like what we have on our notebook. You can see that this guy, this is a huge bias. This guy is just there on its own. The true negative is just dominated. It dominates everywhere. Then the precision recall, they are also there for us to observe, and you can see that the precision recall for class 1 is 0.52, which is terrible, and then for class 0 0.98. So this cannot be accepted, because if we use this model, it will always be predicting 0 as the class. It will hardly predict 1 because of the data samples that we use. Then we look at the ROC curve. We can see that the AUC seems to tell us that everything, or the ROC tells us that everything is fine. Why it's doing that is because it's taking the average of this. So this is not enough for us to justify. We can download the chart from here, but we already know what's wrong with our algorithm, right? So we go and fix it, but that's not for me though, that's for you. You already know what to do. on the sample, and then you get the right result. So pickle model, we didn't include the code to pickle our model. So ideally you include the Neptune provides you the solution for you to put the code in your notebook to extract the trained algorithm and store it on Neptune, but we didn't handle that. Then we have our test result here. You can see these are the test results when it's predicting 0. I think okay, this is y true, y predicted. So these are the prediction for. You can see that there's something I need you to observe. This is y true. The true label is 1, but the predicted is 0. That is the problem with sampling bias. So it keeps lying because because some set of the data set has kind of overshadowed the other part. So zeros have overshadowed ones. Then the probability, the prediction probability is also here, because remember we said logistic regression, everything is based on probability. The probability that it's going to fall into 0, or the probability that it's going to fall into 1 once it crosses the threshold 0.5, according to the chart we used to explain earlier. So that threshold can change, it depends on you. And the class 0 score, we can see the score, the precision score, the recall, the support. And if we go back, and then for 1, you can also see for this. So having done all of this, we can go back and say, okay, let's see monitoring. What do we have there? The CPU usage, the memory usage, all of that, it will be logged in within that time. And then the source code, we can also log our source code into Neptune, but we didn't handle that. Our focus was just to log our data set and also log our training result onto Neptune. Then yeah, you can see the name, the owner of the project, and other things like that. So the same thing you see here, this is all metadata. Similarly, you'll be seeing here. So you come to monitoring, you see it on chart. That is the CPU usage and memory. Then you come to source code. We didn't log the source code, so you can't see anything. Artifacts, you can see the data set we uploaded. So that's all for this guy. I can go ahead and delete it. Delete. Okay. I am not saying you should delete your own. I'm only deleting mine because I've exposed the API token. So I can also delete this because this has also been exposed. So this will be deleted as well, but here this will remain. So after that, we'll go back to our notebook. You have activities to work on. Exercise 4, you import your libraries, you import your random forest classifier, and then what else? You instantiate it inside the step object. Then you go and get your project name or directory, and then the API token. You get them and bring them here. Then you log your files, your training and test files to Neptune. And what else again? Yeah, you log your training summary to Neptune. Of course, whatever you are training, you identify it here. Don't forget to stop the experiment. So that will be all from my end. We'll continue on Slack, and if you have any issue, do let us know. If you have any problem at all, but the only thing I beg of you is to follow the instruction. That's number 1. Number 2, mentorship is both ways. Mentorship is not one directional. I cannot be chasing you to take it serious, so you have to take it serious, and then I have to avail myself to assist you. But if you're not taking it serious, there's no way I can help you. So thank you for your time, and see you on Slack. Bye.